And now we are at basically exam 3, question 3. So now back to exam 1 topic, so hopefully this should be familiar. So let's go ahead and let's get this started. So label all the directions in the plane. So I know, again, this is simple cubic, this is FCC, this is also simple cubic. Label all the directions in the planes. So let's do the planes first, kind of switch it up. So this is my origin, don't want to do that, so I'm going to make this my new origin. So this is my new x, my new y, my new z. So where are my intercepts? X is going to be at -1, y is going to be at 1, z is going to be at infinity. So take the inverse, 1 hat, 1, 0. Got that there. What about here? Same thing. So I'm going to go make this my new origin. So this is my new x. This would be my new y, and that's my z. So what are my intercepts here? X, again, equals -1. Y, where does it intersect my y? Never, so infinity. And then what about my z? 1, so again, 1 hat, 0, 1. So those are all of my planes. So in terms of my directions, I'm going to label this as 1, 2, and 3. So for 1, where's my finish? Basically it's 0, 0, 0, minus 1, 1, 0. So I get 1 hat, 1 hat, 0. So got those. So that's that one there. What about number 2? So in number 2, our finish is going to be basically 1 half, 1 half, 0, minus my start, which is going to be 1, 1, 1. So I'm going to end up with minus a half, minus a half, minus 1, which is going to end up leaving me with 1 hat, and then 2 hat. So that's pretty much that one there. And then finally for number 3, I'm looking at it here. So my finish is 1 half, 1, 1, minus my start, which is basically over here, which is 1 half, 0, 0. So I'm going to end up with 0, 1 hat, actually 0, excuse me here, 1 half, 1 half. Oh, actually, sorry, excuse me, sorry. I am going, that was for my 2, excuse me here. This is 1 half, 1, 1, and then basically going from here to here, and then this is going to be 1 half, 0, 1 half, 0, 0, that's fine. So 0, minus 1, minus 1. Yep, that's it. So got my directions, got my planes. Let's finish that out. What type of unit cell in ABC? FCC, simple cubic, simple cubic. What are my number of atoms? 1, 4, 1. How many number of nearest neighbors? This is going to be 6, 12, 6. What else? What is the lattice parameter? So for simple cubic, A is equal to 2R. For FCC, A is equal to 2R root 2. In terms of R, lattice parameter, draw the closest packed plane as simple cubic here. So the closest packed plane is going to be basically my 1, 0, 0. 1, 0, 0, that's going to be my closest packed plane. Or actually, there's no close packed plane, but that's going to be my closest packed plane. The close packed direction, so there is no official close packed plane. That would be my closest packed plane. My close packed directions would be anything in the 1, 0, 0 direction. So anything like here, here, I'll choose a different color. Here, 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 anything that's not diagonal. So those are indeed close packed directions. Excellent. Write 3 extrinsic reactions incorporating Ta2, basically tantalum oxide, into MgO. So let's go ahead, incorporating my Ta2O5 into MgO. So one must include a substitutional cation and a cation vacancy. So I could write either one first, but I know I'm going to replace. So Ta is going to be on the side where previously Mg was. What's the transition there? So Ta is 5+, so we're going from 2+ to 5+, so that's +3. So 1, 2, 3. plus I need a cation vacancy. So my cation is Mg, so Mg, what's the sign there? That's going to be a -2. So now I have to kind of play around with some charges. So I could go 2 here, I could do 3 here. So that's going to leave me with, now I could start to, I am done with my electroneutrality, but now I need to do my mass balance. So I need to go across, so I have tantalum, so I need 5. Let's go through here. So I need 5 oxygens. So I could go ahead and look through here. 2 tantalum, so I need plus 5 oxygens. Oxygens X. Let's look over here. So I have 2 Mg here, 3 Mg here, so I actually need 5, and that's it. So I'm done there. I need another reaction. Let's erase this now. I need another reaction that must include a cation interstitial and a cation vacancy again. So again, I'm doing Ta2O5 into MgO. What is my cation interstitial? So the interstitial that's being placed in here is this. So that is 1, 2, 3, 4, 5. Plus, I need a cation vacancy, so vacancy in Mg. I can only do vacancy in my host, so that's -2. I need 5 here, I need 2 here. So that gives me 2. I need plus 5 oxygen, oxygen X. And let's look at the mass balance. Perfectly fine. Fantastic. And then finally, actually I need to make sure, I should put the 5 there just to be kind of cautious. Or not to be cautious, to be correct. And then finally we have one more, so let's just get it started. Ta2O5, and make sure you do that Ta2 even on the Mg there. So let's see, anion interstitial, cation vacancy, and cation interstitial. So an anion interstitial into MgO would be oxygen -1, 2, cation vacancy, so vacancy in Mg, that's going to be also -2, and then a cation interstitial, which must be Ta. So I need 1, 2, 3, 4, 5. I need 2 of these, so 2 tantalum. So what can I do now? I could increase the oxygen by 4 here, 4 oxygens, and then I could just do, so that would be 8. Good. So now I can just do plus oxygen, oxygen X. So that would give me here 2 tantalums, 5 oxygens. Excellent. What about below? MgO. Done. So that's it. Finally, for this problem, we are asked to fill out all of the phases in the phase diagram and indicate our invariant points. So my phases will be Ag plus liquid, this plus this, 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 this plus this. This would be beta plus liquid. This is going to be, actually, it's going to 2 phases. This is also going to be beta plus here. This is kind of a funky region. There should be a transition here. This is going to be this material plus liquid. This is going to be this material plus liquid. This is going to be this material plus liquid. This material plus liquid. This material plus liquid. Here it's going to be this material plus liquid. Here it's going to be this material plus liquid. Here it's going to be this material plus liquid. And so you can kind of see where we're going with this. So, but let's do our invariant points. So remember, I'm looking for these types of features. This will give me a eutectic or an oid. An oid will be all solid, so eutectic will be liquid goes to an alpha plus beta. An oid will give me a gamma goes to alpha plus beta. If I'm looking at something like this or something like this, that's peri. And again, if it's tect-ic, so if it's an ic, it's going to be liquid plus alpha goes to a beta, and then I'm going to do, if it's an oid, it's just going to be a gamma plus beta goes to an alpha. So just pure solids. So this one, eutectic. This one, peritectic. What else we got? This is probably eutectic here. This is eutectic here. This is eutectic here. This is eutectic here. Do we have any other values here? I don't think so. So we have quite a few eutectics. We have a congruent melting point here, congruent melting point here, congruent melting point here, congruent melting point here, and that's pretty much it. So that's our phase diagram. So fantastic. Question 3 done. Now we just need to get to question 4 and we're done. Congrats, and I'll see you in the next video. Thanks. Bye.